Now in geometry, the first thing that we'll study is equation of a straight line. So suppose we have a line which passes through 2 points Z1 and Z2, and any general point on this line we'll write as Z. Now this Z is nothing but x plus iota y. Now we need to write equation of this straight line. Now there are many ways with which we can write this equation, and the first way is using section formula. And section formula says if these 3 points are collinear, then Z will divide Z1 and Z2 in some ratio, say m is to n. We can write Z as mz2 plus nz1 upon m plus n. Now if we choose m as t and n as 1 minus t, we can write this Z as tz2 plus 1 minus t z1. So this Z will be z1 plus t into z2 minus z1. So this is one equation of a straight line. Now another way to write equation of straight line is using arguments. So we know that if these 3 points they are in a straight line, then argument of z and z1 and argument of z1 and z2, they must be in the same direction or in opposite direction. So that means we can write argument of z minus z1 upon z2 minus z1, it must be either 0 or pi. Now this is basically argument of z2 upon z1, which is nothing but angle between z1 and z2. So here we are talking about angle between z and z1 and z2 and z1. So this angle, it must be either 0 or pi in case of a straight line. So this is second way to write equation of a straight line. Now we know that if argument of any complex number is 0 or pi, then that complex number is purely real. That means this complex number z minus z1 upon z2 minus z1, it must be a real number. We can write z minus z1 upon z2 minus z1, and this is equal to t. Now we cross multiply, we write z as z1 plus t into z2 minus z1, which again is this first equation. So another way to write equation of straight line is by simply saying imaginary part of z minus z1 upon z2 minus z1 is 0. So another way to write equation of straight line is in terms of its imaginary part. Now we know that if argument is 0 or pi, then it is purely real, and we also know that if a complex number is purely real, then z is equal to z bar. So we can write z minus z1 upon z2 minus z1, it must be equal to z bar minus z1 bar upon z2 bar minus z1 bar. Now we cross multiply, we can write this as z2 bar minus z1 bar z minus z1 z2 bar plus mod of z1 square, and it will be equal to z2 minus z1 z bar minus z2 z1 bar plus mod of z1 square. Now we can cancel this z1 square with z1 square, so we can write this as z2 bar minus z1 bar z minus z2 minus z1 z bar and plus z2 z1 bar minus z1 z2 bar equals 0. Now we can also write this as z2 bar minus z1 bar z minus z2 minus z1 z bar plus z2 z1 bar minus z2 z1 bar whole bar and it is equal to 0. Now this is z minus z bar. Now we know that this is w minus w bar, and we know that w minus w bar upon 2 iota is imaginary part of w. So we can write this as z2 bar minus z1 bar z minus z2 minus z1 z bar plus 2 iota imaginary part of z2 z1 bar will be equal to 0. Now what we will do is we'll divide everything with iota. Now we divide everything with iota, we can write minus iota z2 bar minus z1 bar z plus iota z2 minus z1 z bar plus 2 into imaginary part of z2 z1 bar equals to 0. Now if we take this iota into z2 minus z1 as some complex number a, then this is nothing but this is a bar, and this 2 into imaginary part of z2 z1 bar, it is nothing but some real number b. Then any general equation of a straight line in complex numbers can be expressed as a bar z plus a z bar plus b equals to 0. So if in complex number we have any equation which is like a bar z plus a z bar plus b equals to 0, then this equation will represent a straight line where a is a complex number and b is a real number. So that's our general equation of a straight line. Now another way to write equation of a straight line in complex numbers is using area of a triangle. If z, z1 and z2 they lie on a straight line, then value of this determinant z, z bar 1, z1, z1 bar 1, z2, z2 bar 1, it must be equal to 0. So this is another way of writing equation of a straight line in complex numbers. Now there is this another equation which is very important in straight lines, and it is equation of perpendicular bisector of z1 and z2. So suppose we have two complex numbers a and b which are represented by z1 and z2, and if we have to write equation of this perpendicular bisector line, we know that any point on the perpendicular bisector, it will be equidistant from both the 2 points. That means AP, it must be equal to PB. Now say this point is Z. Now in complex number, any distance, it is given by modulus. So this distance AP is mod of Z minus Z1, and this PB is Z minus Z2. So another way to write equation of straight line. So if we are given any equation which is mod of Z minus Z1 equals mod of Z minus Z2, it again represents the straight line, which in this case is equation of perpendicular bisector of AB. And in some cases, they may also write it as mod of Z minus Z1 upon Z minus Z2. If it is equal to 1, then this equation will represent a straight line which is perpendicular bisector of Z1 and Z2. But in that case, mind it, coefficient of Z, it must be 1 in both numerator and denominator. If it is not 1, then it may not represent a straight line. Now here the question is, let Z1 and Z2 be two distinct complex numbers. So we have two distinct complex numbers, Z1 and Z2. Now it says there is some complex number Z such that Z is 1 minus t Z1 plus t Z2. So we'll take a point Z which divides Z1 and Z2 in the ratio t is to 1 minus t. So we can write this Z as t Z2 plus 1 minus t Z1 upon 1. Now since t, it lies between 0 and 1, this point Z, it will lie between Z1 and Z2. So it simply means that this Z, it lies on this line segment, let us say AB, and suppose this point is P. Now these 3 points AP and B, they are collinear. We can write AP plus BP, it is equal to AB. Now AP is mod of Z minus Z1, BP is mod of Z minus Z2, and AB is mod of Z1 minus Z2. That means option A is correct. Now we look at argument of Z minus Z1. Now Z minus Z1, it is this vector, and Z minus Z2 is this other vector. Now argument of Z minus Z1 is not equal to argument of Z minus Z2, as these two vectors, they are in opposite direction. So that means option B is incorrect. Now what about argument of Z minus Z1 and argument of Z2 minus Z1? Now Z2 minus Z1 and Z minus Z1, both of them, they're in the same direction. So from here we can say argument of Z minus Z1, it must be equal to argument of Z2 minus Z1. That means this option D is correct. Now from this, if we take everything on the left hand side, then argument of Z1 minus argument of Z2 is argument of Z1 upon Z2. So from here we can say argument of Z minus Z1 upon Z2 minus Z1, it must be 0. Now if argument is 0, that means this complex number is purely real. And if the complex number is purely real, then Z equals Z bar. So we can write Z minus Z1 upon Z2 minus Z1, it must be equal to Z bar minus Z1 bar upon Z2 bar minus Z1 bar. Now if we cross multiply, we can write Z2 bar minus Z1 bar into Z minus Z1, and it must be equal to Z2 minus Z1 into Z bar minus Z1 bar. That means this option C is also correct. So the correct options are A, C and D. Now we'll come to complex slope of a line. So suppose we have a line which passes through 2 points Z1 and Z2, then complex slope of this line is defined as mu, and is given by Z1 minus Z2 upon Z1 bar minus Z2 bar. So if we are given 2 points on this line, say A and B, which are given by Z1 and Z2, then complex slope of this line, which is mu, it is given by Z1 minus Z2 upon Z1 bar minus Z2 bar. And if we are given general equation of a straight line, which is AZ bar plus A bar Z plus B equals to 0, in that case, this complex slope, it is given by minus A upon A bar. Now here the question is, if Z1 and Z2 are two complex numbers representing points A and B, we define complex slope of line AB as mu Z1 minus Z2 upon Z1 bar minus Z2 bar. So we have a straight line passing through 2 points Z1 and Z2, and we have defined complex slope mu as Z1 minus Z2 upon Z1 bar minus Z2 bar. Now we need to find complex slope of this line, which is A bar Z plus AZ bar plus B equals 0. Now in straight lines, we have already proved that equation of a straight line which passes through Z1 and Z2 is given by Z into iota Z1 bar minus Z2 bar plus minus iota Z1 minus Z2 into Z bar and minus 2 imaginary part of Z1, Z2 bar equals 0. Now we compare it with the standard equation. This is your A bar and this is A. Now if we find A upon A bar, it will be minus iota Z1 minus Z2 upon, and A bar is iota Z1 bar minus Z2 bar. Now this iota will cancel, and this expression, it is nothing but mu. So it will be minus mu. So its complex slope will be simply minus A upon A bar, and that's your option C. Now question number 36 is, if mu and mu dash are complex slopes of two perpendicular lines, then which of the following is correct? So now we have two perpendicular lines. One of them passes through, say, Z1 and Z2, and the other one it passes through Z3 and Z4. Now mu is Z1 minus Z2 upon Z1 bar minus Z2 bar, and mu dash is Z3 minus Z4 upon Z3 bar minus Z4 bar. Now since these two lines, they are perpendicular, we can write argument of Z1 minus Z2 upon Z3 minus Z4, it is plus or minus pi by 2. And if argument is plus minus pi by 2, it means this complex number, it is purely imaginary. And if the complex number is purely imaginary, then Z equals minus Z bar. So from here we can write Z1 minus Z2 upon Z3 minus Z4 will be Z1 bar minus Z2 bar upon Z3 bar minus Z4 bar, and this minus sign. Now if we rearrange it, we can write this as Z1 minus Z2 upon Z1 bar minus Z2 bar, and it will be equal to minus Z3 minus Z4 upon Z3 bar minus Z4 bar. So this is mu is equal to minus mu dash, or we can write mu plus mu dash equals 0. So answer to question number 36 is mu plus mu dash equals 0, and that's your option C. Now the next one is, if these two lines are parallel, then what? If the two lines are parallel, then in that case, this argument, it won't be pi by 2, it will be simply 0 or pi, and if it is 0, then it is purely real. And if the complex numbers are purely real, then Z is equal to Z bar. So we won't have this minus sign here. From this we can write Z1 minus Z2 upon Z1 bar minus Z2 bar will be equal to Z3 minus Z4 upon Z3 bar minus Z4 bar. That is, mu is equal to mu dash, and that's your option A. Now question number 38 is, if a line makes an angle theta with positive direction of x-axis, then its complex slope equals what? So here we are given that there is a line which makes an angle theta with positive direction of x-axis. Now suppose we have 2 points here, Z2 and Z1. Now argument of Z1 minus Z2 is theta. That means Z1 minus Z2 will be some r into e to the power iota theta. Now if we take its conjugate, it will be Z1 bar minus Z2 bar will be r into e to the power minus iota theta. Now if we divide first with second, we'll get Z1 minus Z2 upon Z1 bar minus Z2 bar. Now here r and r will cancel, so it will be e to the power iota 2 theta, and this is your mu. So in that case, the complex slope will be e to the power 2 iota theta, and that's your option A. Now the next one is length of perpendicular from a point to the line. So suppose we have this line which is given by AZ bar plus A bar Z plus B equals 0, and then we have a point, say Z0, and we need to find perpendicular distance of this point from this line. Now suppose this A is some P plus iota Q and Z is X plus iota Y. Now we can write this as P plus iota Q and Z bar will be X minus iota Y, and here will be P minus iota Q, X plus iota Y, and plus B equals 0. So we can write this as Px plus Qy minus P iota Y plus iota Qx will be Px plus Qy plus iota Py minus iota Qx plus B equals 0. Now this iota Py and iota Qx will cancel, so we'll get this equation as 2Px plus 2Qy plus B equals 0. So that is the equation of this straight line. Now we have to find perpendicular distance of this point Z0, which is given by, say, X0 and Y0 from this line. We know that this perpendicular distance will be given by this mod 2Px0 plus 2Qy0 plus B upon under root of 4P square plus 4Q square. Now this 2Px0 plus 2Qy0 plus B, it is nothing but, it is the same expression which is AZ bar plus A bar Z plus B when the value of Z is Z0. It will be AZ0 bar plus A bar Z0 plus B and its modulus upon, now here we'll take 2 common and will be under root of P square plus Q square, which is mod of A. So perpendicular distance of this point Z0 from this line will be A Z0 bar plus A bar Z0 plus B upon 2 mod A and this whole modulus. So this is how we can find length of perpendicular from a point to a line in complex numbers. There could be questions on angle bisector also. Now in vectors we know that if we are given two vectors A and B, then its internal angle bisector, it is given by A cap plus B cap. Now we'll use the same fundamental here. Suppose we have two complex numbers Z1 and Z2. Now Z1 is, suppose R1 e to the power iota theta 1 and Z2 is, suppose R2 e to the power iota theta 2. Now this angle is theta 1 and this angle is theta 2. Now this angle is theta 2 minus theta 1. Now we look at its angle bisector. This angle now will be theta 2 minus theta 1 by 2. So this entire angle from positive real axis, which is say alpha, it will be theta 1 plus theta 2 by 2. Any complex number in this internal angle bisector direction, which is say Z, will be given by some R and then e to the power iota theta 1 plus theta 2 by 2. Now here the question is, if P is cos theta comma sin theta and Q is cos alpha minus theta comma sin alpha minus theta, then Q is obtained from P by which of the following transformations? So in this question what we are given is, we are given a point P And let us say this point P is e to the power iota theta. Now if we take its reflection about real axis, then we'll get this point which is say P dash, and it'll be e to the power minus iota theta. So this angle is theta and this angle is also theta. Now what we'll do is we'll rotate this vector OP dash by an angle alpha. Now this point will be e to the power iota alpha minus theta, and which is nothing but q. Now if we look at this angle is 2 theta minus alpha, and this angle it is alpha minus theta. Now if we take angle bisector of OP and OQ, then this angle will be theta minus alpha by 2. So basically this point Q is reflection of P about this line. Now we need to find equation of this line. So for that we have to find its slope, and for its slope we have to find this angle. Now this angle is alpha minus theta and this angle is theta minus alpha by 2. So this angle, which is say phi, it will be alpha minus theta plus theta minus alpha by 2, which is alpha by 2. So equation of this line will be y equals m, which is 10 alpha by 2 into x. So this q, it is obtained from P by taking the reflection in the line through origin whose slope is 10 alpha by 2, and that's your option D. Now we'll discuss reflection of a point in a line. Now suppose we have this line, say AB, and we have a point Z, and we need to find reflection of this Z in this straight line AB. Now suppose this reflection is W, and suppose A and B, they are given by complex numbers, say AB. Now we need to find W in terms of AB and Z. Now we know that this angle is 90, so we can write argument of W minus Z upon B minus A will be plus or minus pi by 2. And if argument is 90, that means that complex number is purely imaginary. And if it is purely imaginary, then Z equals minus Z bar. So we can write W minus Z upon B minus A will be minus W bar minus Z bar upon B bar minus A bar. We'll get the same condition from complex slopes also. We can write mu1 plus mu2 equals 0. We'll end up getting the same condition. Now we cross multiply. We can write this as B bar minus A bar W minus Z B bar minus A bar, and L B minus B minus A W bar plus B minus A Z bar. So we can write this equation as B bar minus A bar W plus B minus A W bar, and L B equal to B minus A Z bar plus B bar minus A bar Z, and that's our first equation. Now this midpoint, it is Z plus W by 2. Now let this point be C. Now since ABC, they are collinear, complex slope of AC must be equal to complex slope of AB. So we can write Z plus W upon 2 minus A upon Z bar plus W bar upon 2 minus A bar, and LB equal to B minus A upon B bar minus A bar. Now we'll multiply and divide it with 2. We can write Z plus W minus 2A upon Z bar plus W bar minus 2A bar will be equal to B minus A upon B bar minus A bar. Now we cross multiply, we can write this as B bar minus A bar W minus B minus A W bar. Now will be equal to B minus A Z bar minus B bar minus A bar Z plus 2AB bar minus 2A bar B, and that's our second equation. Now we need to find this W. So what we'll do is we'll add these two equations, then this B minus A W bar will cancel. So we can write 2 times B bar minus A bar W, and will be equal to 2 times B minus A Z bar. This B bar minus A bar Z will also cancel, and then plus 2 AB bar minus A bar B. I will cancel this 2 with 2. We can write W as B minus A Z bar plus AB bar minus A bar B upon B bar minus A bar. And that is the formula for image of a point in a line. Now here the question is, let B bar Z plus BZ bar equal C be a line in the complex plane. So we have a line which is B bar Z plus BZ bar equals C. If a point Z1 is the reflection of point Z2 through the line, so we have 2 points Z1 and Z2, and Z1 is reflection of Z2 in this line, then we need to show that this C is equal to Z1 bar B plus Z2 into B bar. Now this line is basically perpendicular bisector of Z1 and Z2, and we know that equation of perpendicular bisector is given by mod of Z minus Z1 equals mod of Z minus Z2. Now we square it, we can write Z minus Z1 into Z bar minus Z1 bar, it is equal to Z minus Z2 into Z bar minus Z2 bar. Now we multiply it, we'll write ZZ bar minus Z1 Z bar minus Z1 bar Z plus mod of Z1 square, and on the right hand side we'll have ZZ bar minus Z2 Z bar Z2 bar Z plus mod of Z2 square. Now we'll cancel this ZZ bar, we can write this as Z2 minus Z1 into Z bar plus Z2 bar minus Z1 bar Z, and it is equal to mod of Z2 square minus mod of Z1 square. Now if we compare it with this given line, that means this is B, this is B bar, and this is your C. Now first we'll find Z bar B plus Z2 B bar. So Z1 bar B plus Z2 B bar, it will be Z1 bar, and B is Z2 minus Z1 plus Z2 into Z2 bar minus Z1 bar. So it will be Z1 bar Z2 minus mod of Z1 square plus mod of Z2 square minus Z2 into Z1 bar. Now this will cancel. We get this as mod of Z2 square minus mod of Z1 square, which is nothing but C. So from here we can say this is possible when this C is Z1 bar B plus Z2 B bar, and this is what we need to prove. Now here the question is, let M be a line in the complex plane defined by 1 minus iota Z plus 1 plus iota z bar, and it is equal to 4. Now let z is 2 plus 2 iota, and it says if reflection of z1 in M is z2, then we need to find this value. Now if we look at this equation, we can write this equation as b bar z plus bz bar, and it is equal to c, where the value of b is 1 plus iota and value of c is 4. Now if reflection of z1 is z2, then we have already established that this c equals z1 bar b plus z2 b bar. Now here we can write z1 bar, and what's b? b is 1 plus iota and plus z2, and b bar is 1 minus iota, and we know that it is nothing but c. Value of c here is 4. So answer to this question is simply 4. Now here the question is, we need to find reflection of this line in the real axis. Now first we'll draw the axis, and then we'll draw this line, and this line will pass through origin. So this line is a bar z plus az bar equals 0. Now we need to find equation of reflected line. Now let us take this point as z. Now if this point is z, then reflection of z about real axis will be z bar, and z bar will lie on this line. We can write a bar z bar plus az equals 0. So locus of z will be this straight line, which is a bar z bar plus az, and that's your option A. Now the next one is equation of a circle. Definition of a circle is locus of all the points which are equidistant from a given fixed point. So suppose the fixed point is center of the circle, and it is at z0, and the fixed distance is radius r. So we have to write equation of a circle whose center is z0 and whose radius is r. Then we know that any point on this circle which is z will be at a distance r from z0. Now distance, it is given by mod, so it will be mod of z minus z0, and it must be equal to r. And this is your equation of circle. So equation of any circle whose center is z0 and whose radius is r will be given by this mod of z minus z0 equals r. Now say for example, suppose we have to plot this circle which is mod of z plus 1, it is equal to 1. Now we can write this as z minus of minus 1, it is equal to 1. So represent a circle whose center is at minus 1 and whose radius is 1 units. So it will be this circle with center at minus 1 and radius 1 unit. Now there will be times where you will be given points not only on the circle but on the inside or outside the circle. So one such case could be when they are going to write mod of z minus z0 is less than equal to r. In that case, it will represent all the points on or inside the circle whose center is z0 and whose radius is r. And if the question is mod of z minus z0, it is greater than or equal to r, then in that case represent all the points on the circle with center z0, radius r, and points lying outside this circle. Now here the question is, if the complex number z is such that mod z minus 1 is less than or equal to 1. So we have coordinate axis, and then we have a circle whose center is at 1 and whose radius is also 1. So we are talking about all the points on or inside this circle. Now this point is 0 and this point is 2. Now the second one is mod z minus 2 equals 1. So this again is a circle with center at 2 and radius equals 1 unit. So all the complex numbers which satisfy both these conditions are this portion of second circle which lies inside or on this first circle. Now we know that maximum value of mod z will occur at this point. So this is maximum value of mod z. Now we drop a perpendicular. This is 1 unit. This is radius of this circle, which is 1 unit, and this length is 1 by 2. So we can find this d. This d will be under root of 1 minus 1 by 4 and will be root 3 by 2. Now we can find maximum value of mod z. Now this is d and this length is 1 plus 1 by 2 and will be 3 by 2. So this mod of z max square, it will be 3 by 2 square plus root 3 by 2 square. Now this is 9, 9 plus 3, 12. 12 upon 4 is simply 3. So the maximum possible value of z square is 3, and that's your answer to this question. So now we have studied that equation of circle is mod of z minus z naught equals r. Now another way to write this equation is we can square it. We can write mod of z minus z naught square, it is equal to r square, and we know that mod of z square is z into z bar. We can write this as z minus z naught into z bar minus z naught bar, and it is equal to r square. Now we'll write this as z bar minus z naught bar z minus z naught z bar plus mod of z naught square minus r square equals 0. Now we take minus z naught as a, which is some complex number. This is some b, which is real number. We can write this equation as z bar plus az bar plus a bar z plus b equals 0. So if in complex numbers we have this equation which is z bar plus az bar plus a bar z plus b equals 0, then it will represent a circle whose center is at z naught, which is minus a. So center of this circle will be at minus a, and its radius will be r square, which is mod of z naught square minus b, or we can write its radius will be under root of mod of a square minus b. So if we come across any equation which has z bar plus az bar plus a bar z plus b equals 0, then it will represent a circle whose center is at minus a and whose radius is under root of mod of a square minus b. So that is second way to write equation of this circle. Now third way to write equation of a circle is in terms of Apollonius circle, which is ratio of any point on the circle from two fixed points. If it is constant and unequal to 1, then the locus of this point will be a circle. So basically we'll be given this condition that mod of z minus z1 upon z minus z2, it is equal to k, and this k is unequal to 1. Now we have already studied in straight lines. If the value of k is 1, then in that case it will represent a straight line which is perpendicular bisector of z1 and z2. But if this k is unequal to 1, then in that case this equation will represent a circle. Basically we can simplify it to prove it is equation of circle. So what we'll do is we'll square it again. We'll write mod of z minus z1 square will be equal to k square mod of z minus z2 square. Now this is z minus z1 into z bar minus z1 bar, and will be equal to k square z minus z2 into z bar minus z2 bar. Now we multiply it. We'll write z bar minus z1 bar z minus z1 z bar plus mod of z1 square, and it will be equal to k square z bar minus z2 bar z minus z2 z bar plus mod of z2 square. Now we take everything on the left hand side, then we can write 1 minus k square z bar minus z1 bar minus k square z2 bar z minus z1 minus k square z2 z bar plus mod of z1 square minus k square mod of z2 square equals 0. Now if this k it is equal to 1, then we won't have this z bar term. Then we can write this as a z bar plus a bar z plus b equals to 0, which is equation of a straight line. So if this k is equal to 1, then this equation it will represent a straight line. But if this k it is unequal to 1, we can write this as z bar minus z1 bar minus k square z2 bar upon z upon 1 minus k square minus z1 minus k square z2 upon 1 minus k square z bar plus mod of z1 square minus k square mod of z2 square upon 1 minus k square equals 0, which is z bar plus a bar z plus a z bar plus b equals to 0, which is equation of a circle. So basically if this k is unequal to 1, then this equation will represent a circle, and basically this circle will be Apollonius circle. Now the fourth way to write equation of a circle is if we are given n points of a diameter. So suppose we have a circle whose diameter is AB, which is given by Z1 and Z2. Then for any point on this circle P, we know that this angle in a semicircle is 90 degrees. So this triangle APB will be a right angle triangle, and if this P is given by Z, then we can write AP square plus BP square, and it must be equal to AB square. Now AP is distance between A and P. We can write this as mod of Z minus Z1 square, and BP is mod of Z minus Z2 square, and it will be equal to mod of Z1 minus Z2 whole square. So if we have any equation where we have mod of Z minus Z1 square plus mod of Z minus Z2 square, and it is equal to mod of Z1 minus Z2 whole square, it will represent equation of a circle. Another way to write the same equation is using argument. Now we know that this angle, it is 90 degrees. Now we can write angle between these two complex numbers, Z1 minus Z and Z2 minus Z. Then this angle, it must be pi by 2. So another way to write equation of the same circle is in terms of argument. So if argument of Z minus Z1 upon Z minus Z2, it is plus or minus pi by 2, then this Z will lie on a circle whose n points of diameter are Z1 and Z2. Now if we take only plus sign or only minus sign, in that case it will represent only a semicircle. And previously we have studied if this argument Z minus Z1 upon Z minus Z2, it is 0 or pi, then this Z, it will lie on a straight line. So if it is 0 or pi, it's a straight line, and if it is plus minus pi by 2, then this Z, it will lie on a circle whose n points of diameter are A and B. Now another way to write the same equation is, now we know that its argument is plus or minus pi by 2. Now when the argument is plus or minus pi by 2, we know that this complex number, it must be purely imaginary. So we can write Z minus Z1 upon Z minus Z2, it is purely imaginary. So another way to write this equation is in terms of its real part. So if real part of z minus z1 upon z minus z2 is 0, then again represent the equation of this same circle. And if imaginary part is 0, then we already know it will represent a straight line. Now, seventh way to write this equation is in terms of its conjugate. Now we already know that z minus z1 upon z minus z2 is purely imaginary. And if the complex number is purely imaginary, then z is equal to minus z bar. So we can write z minus z1 upon z minus z2 will be equal to minus z bar minus z1 bar upon z bar minus z2 bar, and we can rearrange this as z minus z1 into z bar minus z2 bar, and it will be equal to minus z minus z2 into z bar minus z1 bar. Now we take everything on the left hand side, we can write z minus z1 into z bar minus z2 bar plus z bar minus z1 bar into z minus z2 equals 0. So this equation again will represent equation of a circle whose end points of diameter are z1 and z2. Now this eighth equation is not equation of a complete circle, but basically equation of a portion of a circle. Now suppose we say we have a circle whose chord is say AB, where A is given by Z1 and B is given by Z2. Now suppose this angle is alpha. Now we know that angle in the same segment is same. So this angle will be alpha irrespective of position of Z for this segment. For the other segment, it will be pi minus alpha. So if we write argument of Z minus Z2 upon Z minus Z1 equals to alpha, this equation again will represent a circle. Not a complete circle, but portion of the circle. That is the segment where this angle is alpha. So this equation will represent part of a circle except when alpha is 0 or pi. Now we need to find mirror image of this curve given by argument z plus iota upon z minus 1 equals pi by 4 in the line y equals x. Now what we are given is we are given argument of z plus iota upon z minus 1 equals pi by 4. Now we can write this as tan inverse y plus 1 by x minus tan inverse y upon x minus 1, and it will be pi by 4. Now we'll use tan inverse a minus tan inverse b. We can write tan inverse y plus 1 upon x minus y upon x minus 1 upon 1 plus y plus 1 y upon x into x minus 1, and it is pi by 4. Now we'll take tan inverse to the right hand side. We can write xy minus y plus x minus 1 minus xy, and it will be equal to x square minus x plus y square plus y. Now this xy will cancel. We can write this as x square plus y square minus 2x plus 2y plus 1 equals 0. Now center of the circle is at 1 comma minus 1, and its radius will be 1 unit. So it will be this circle. This is 1 comma minus 1 and radius is 1 unit. Now we have to take reflection of the circle about y equals x line. So if we take reflection of the circle about y equals x line, now for this New circle, center will be at -1, 1 and radius will be 1. Now for this given circle, this point of contact is minus iota and 1, and for this circle, contact is -1 and iota. So it has to be argument z minus iota upon z plus 1 equals pi by 4, and that's your option C. Suppose z is such that argument of z plus iota upon z minus iota, it lies between pi by 3 and 2 pi by 3, then locus of z is shaded region in adjacent figure. So we need to draw this shaded region. Now if we look at argument of z minus of minus iota upon z minus iota, and it is equal to some angle alpha. We know that this represents portion of a circle with chord passing from iota and minus iota and making an angle alpha. So what we'll do is we'll draw the axis, and then we have 2 points, iota and minus iota. Now if we consider a circle passing through iota and minus iota, then at any point z, this is z minus of minus iota, z minus iota, and this angle will be alpha. Now it says this angle, it must lie between pi by 3 and 2 pi by 3. So we have to draw this region, then we have to draw 2 circles. First circle in which it makes an angle pi by 3, and then this second circle at which it makes an angle 2 pi by 3. This again is iota, this is minus iota, this angle is pi by 3, and this angle is 2 pi by 3. So we need all the points z such that this argument, it always lie between pi by 3 and 2 pi by 3. That means we are talking about the region in between these 2 circles. So the locus of z is represented by this region within these 2 circles. Now here the question is, if z is any complex number satisfying mod of z minus 3 plus 2 iota less than or equal to 2, then we need to find minimum value of mod 2z minus 6 plus 5 iota. Now first we'll draw this region. Now this is your axis. Now this region, it represents all the points on or inside the circle whose center is at 3 plus 2 iota and radius equals 2 units. This is 2 units. So we are talking about all the points on or inside this circle. Now we need to find minimum value of 2z minus 6 plus 5 iota. Now what we'll do is we'll take this 2 out, then we can write z minus, and it'll be 3 minus 5 by 2 iota. Now this is modulus, and any modulus is nothing but distance between 2 points. So here we are talking about distance between z and this point, which is 3 minus 5 by 2 iota. Now 3 minus 5 by 2 iota will be this point. So this is 3 minus 5 by 2 iota. Now we need to find this minimum distance. Now minimum distance is given by this value, and this value is nothing but 5 by 2. So minimum value of this modulus function will be 2 times 5 by 2, and which is 5. So answer to this question is simply 5. Now here the question is, let z1 and z2 be 2 complex numbers satisfying mod z1 equals 9 and mod of z2 minus 3 minus 4 iota is equal to 4. Then minimum value of mod z1 minus z2 is. Now we'll draw the axis. Now this first complex number Z1, it will lie on a circle with center at origin and radius equals 9 units. So it will be this circle. So center at origin, and this is 9 units. Now Z2 will lie on a circle whose center is at 3 plus 4 iota. So it will be at 3 plus 4 iota, and its radius is 4. So it will be this circle with center at 3 plus 4 iota. Now it says we need to find minimum value of mod Z1 minus Z2. Now Z1, it lies on this outer circle, and Z2, it lies on this smaller circle, and we know that any modulus is nothing but distance. So we need to find minimum distance between these two circles, and we know that minimum distance, it will occur along the line joining their centers. So this distance, it is minimum. So minimum value of Z1 minus Z2 will be given by this radius, which is 9, and then minus this distance, which is 5 units, and then plus this radius, which is 4. So 9 minus 9, which is 0. So minimum value of mod Z1 minus Z2, it must be 0. So these two circles, basically, they'll touch each other. And that is the answer to this question. Let us take another question, in which is, let Z1 is represented by set of all points which are mod Z1 equals 12, and Z2 is given by set of points which is mod Z2 minus 3 minus 4 iota equals 5. We need to find minimum and maximum value of mod Z1 minus Z2. Now, first one is Z1. So mod Z1 equals 12. That means Z1 will lie on a circle with center at origin and radius equals 12 units. So Z1 will lie on this circle with center at origin and radius equals 12 units. And for the second one, we know that its center is at 3 plus 4 iota and its radius is 5. So it will be this circle with center at 3, 4 and radius equals 5 units, and this is your Z2. Now we need to find minimum and maximum value of mod Z1 minus Z2. Now mod Z1 minus Z2 is nothing but distance between Z1 and Z2. Now the minimum distance between Z1 and Z2, it will be along the line joining their centers, and it will be this distance. So value of mod Z1 minus Z2 minimum, it will be this entire distance, which is radius of this larger circle 12 minus diameter of this smaller circle, which is 10. So it should be 2 units. And maximum value of Z1 minus Z2 will again occur along this line, and it is this distance. Now this distance is 12 units and length of diameter is 10. So it will be 12 plus 10, which is 22 units. So the minimum value of Z1 minus Z2 is 2 and its maximum value is 22. Now here the question is, if Z is a complex number such that mod of Z is greater than or equal to 2. So in this case, it will represent all the points on or outside the circle with center at origin and radius equals 2 units. So it will contain all the points on or outside this circle with center at origin and radius equals 2 units. Now it says we need to find minimum value of mod Z plus 1 by 2. Now we know that any modulus is nothing but distance between 2 points. Now we are looking for distance between Z minus of minus 1 by 2. So we need to find minimum distance between minus 1 by 2 and all these points lying on the circle or outside this circle. So the minimum distance will be this distance. So minimum value of z plus 1 by 2, it will be this 2 minus 1 by 2, and it will be nothing but 3 by 2. So this minimum value, it will lie in the interval 1, 2, and that's your option B. Now here the question is, if mod of z plus 4 is less than or equal to 3, we need to find maximum value of mod z plus 1. Now this is nothing but a circle with center at -4 and radius equals 3 units. So it'll represent all the points on or inside this circle. Now this point is -7 and this is -1. Now we need to find maximum value of mod z plus 1. Now mod z plus 1 is distance between z and -1. So this is -1, and the point which is farthest from this point is this other point. So maximum value of this modulus will be diameter of this circle, which is 6, and that's your option 1. What about minimum? Minimum will be this point itself, and it will be 0. Now here the question is, among the complex numbers z, find z which satisfy mod of z minus 25 iota is less than or equal to 15 and having least positive argument. So we'll draw the axis. And then we have points on or inside this circle with center at 25 iota and radius equals 15 units. So this is 25 and this is 15. Now it says we have to find that complex number z having least positive argument. So here argument is 90, and if we move towards right, argument keeps decreasing. We'll have least positive argument when this line will be tangent to this circle. So we are looking for this point, say z. Now this is 90, this is 25, and this is 15. We'll find the value of r. Now r square will be 25 square minus 15 square, that is 625 minus 225, that is 400. That is the value of r, it must be equal to 20. Now we'll find this theta also. Now if this is theta, this is 90 minus theta, this again is theta. Now we can write this z as r cos theta plus iota sin theta. So this z will be r, which is 20. Now cos theta. Now in this right angle triangle, cos theta is 15 by 25, which is 3 by 5 plus iota, and sin theta will be simply 4 by 5. So it will be 4. So that should be 12 plus 16 iota. So this complex number z having least positive argument will be 12 plus 16 iota. Now here the question is, let S denote set of all complex numbers satisfying this inequality mod of z minus 5 iota equals 3. So we'll draw this region, which is set of all points lying on or inside this circle with center at 5 iota and radius equals 3 units. Now this distance is 5 and radius is 3. Now let's say find the complex number z having least positive argument and maximum positive argument. Now least positive argument will be when it is tangent to this right side, and it will be maximum positive argument when it will be tangent to this left hand side. Now this is 5, radius is 3 units, so it will be this 4 unit. It will be this 4. Now we need to find z1 and z2. Now suppose this angle is theta, this angle will also be theta. So we can write z1 as 4 cos theta plus iota sin theta. So it will be 4. Now what is cos theta? Cos theta is 3 by 5 and sin theta is 4 by 5. So it will be 12 by 5 plus 16 iota by 5. So this is the complex number having least positive argument. Now from symmetry we can say this Z2 will be at minus 12 by 5 and then plus 16 by 5 iota. Now it says we need to find Z having least modulus. Now least modulus will be this point and this point will be 5 and this distance is 3. So it will be simply 2 iota, and Z with maximum modulus will be this point, which is simply, this is 2 plus 6 is 8. So it will be simply 8 iota. Now here the question is, find the equation of circle in complex form which touches the line iota Z plus Z bar plus 1 plus iota and 2 minus iota Z equals 2 plus iota Z bar and 2 plus iota Z plus iota minus 2 Z bar minus 4 iota. Now here the question is, find the equation of circle in complex form which touches this given line iota Z plus Z bar plus 1 plus iota equals 0, and for which these two lines, they are normals of the circle. Now we know that normals intersect at center of the circle. So what we'll do is, we'll solve these two equations, which are 2 minus iota Z equals 2 plus iota Z bar and 2 plus iota Z plus iota minus 2 Z bar minus 4 iota equals 0 to find center of the circle. From this first equation, we'll write Z bar and it will be 2 minus iota upon 2 plus iota Z. Now we'll put it in the second equation. We can write 2 plus iota plus iota minus 2 into 2 minus iota upon 2 plus iota whole Z, and it will be equal to 4 iota. Now we'll solve it. We'll get 4 minus 1 plus 4 iota, and it will be minus 4 minus 1 minus 4 iota upon 2 plus iota Z, and it will be equal to 4 iota. Now 4 and minus 1 will cancel. We'll get this as 8 iota, which is 2. So value of Z will be 2 plus iota upon 2 or 1 plus iota by 2. So center of this circle, it will be at 1 plus iota by 2. Now once we have the center, we need to find its radius, and for that we'll first find equation of tangent. We can write this as iota x plus iota y plus x minus iota y plus 1 plus iota equals 0. So it will be iota x minus y plus x minus iota y plus 1 plus iota equals 0. Now we compare real and imaginary part. We can write this equation will be x minus y plus 1 equals 0. So equation of this tangent is x minus y plus 1 equals 0. Now we need to find its radius. Now radius is nothing but perpendicular distance from center to this tangent. Now center of this circle is at 1 comma 1 by 2. So it will be 1 minus 1 by 2 plus 1 upon root 2. So it will be 3 upon 2 root 2. Now once we have center and radius, we can write equation of this circle as mod of Z minus 1 plus iota upon 2, and it will be equal to 3 upon 2 root 2. And that's your option C. Now here the question is, let A and B be sets defined by mod of Z is less than or equal to 2. That means all the points on the circle whose center is at origin and radius is 2 units. So this A, it consists of all these points. Now B is 1 minus iota z plus 1 plus iota z bar. It is greater than or equal to 4. Now we can write this as 1 minus iota and it is x plus iota y, and it is 1 plus iota and x minus iota y, it is greater than or equal to 4. Now we can write this as x plus y minus iota x plus iota y, and here also it will be x plus y plus iota x minus iota y, it is greater than or equal to 4. So these two will cancel. So we'll get x plus y is greater than or equal to 2. Now this point is 2, 0 and this point is 0, 2. So if we draw this line is x plus y equals 2. Now we need the points where x plus y is greater than or equal to 2. Now if you put origin, we'll get 0 is greater than or equal to 2, which is false. That means it has all the points which lie on the right of this line. Now area common to both A and B is area of this segment. So area of this segment will be 1 by 4 into pi r square minus 1 by 2 into r square. Now r square is 4. So we get this is pi minus 2. So this area of region A intersection B will be pi minus 2 square unit. Now here the question is, let z be a complex number having the argument theta and satisfying the equality mod of z minus 3 iota equals 3. Then we need to find the value of cot theta minus 6 upon z. Now z lies on this circle with center at 3 iota and radius equals 3. So we'll draw this circle. Now this is 3 iota. Now it says its argument is theta. So we'll take this point on this circle and this point is z and its argument is theta. Now we know that this is 90, this is 6 units and this angle is theta. Now for this complex number z, if we find r, this r, it will be 6 sine theta. So we can write r as 6 sine theta. So once we have r and theta, we can write z as r, which is 6 sine theta into cos theta plus iota sine theta. Now we can rearrange it as 6 upon z and it will be equal to 1 upon sine theta into cos theta plus iota sine theta, and if we rationalize it, we can write this as cos theta minus iota sine theta upon sine theta, which is cot theta minus iota. Now if we rearrange it again, we can write cot theta minus 6 upon z and it will be equal to iota, and that's your option C. Now here the question is, if one of the vertices of the square circumscribing the circle mod of z minus 1 equals root 2 is 2 plus root 3 iota, then find the other vertices of this square. So we have this circle whose center is at 1, 0 and whose radius is root 2. That says there is a square which is inscribed in this circle. And one of the point is 2 plus root 3 iota. Now we need to find other vertices of this square. Now we know that the vertex which is opposite to this given vertex, it will have its midpoint at 1. So suppose this is z1. Now z1 plus 2 plus root 3 iota upon 2, it is 1. That means value of z1 will be minus root 3 iota. So this vertex will be minus root 3 iota. Now what about the other two vertices? This is z2. Now if we use rotation, we can write z2 minus 1 upon 2 plus root 3 iota minus 1. So it will be 1 plus root 3 iota, and it will be equal to e to the power iota plus or minus pi by 2. So it will be simply plus or minus iota. So we can write z2 minus 1 will be plus minus iota and then minus plus root 3. So other two vertices, there will be 1 minus plus root 3 and plus or minus iota. So this is how we can write all the 4 vertices of this square. Now here the question is, if the complex number PW lies on a standard unit circle in an Argand plane and Z is AW plus B upon W minus C, then find the locus of Z and interpret it given that A, B, C are real numbers. Now if we cross multiply, we can write WZ minus CZ, it is equal to AW plus B. So we can write W as CZ plus B upon Z minus A. Now it is given that this W lies on a standard unit circle. That means mod of W equals 1. So from here we can write mod of CZ plus B upon Z minus A, it is 1. Now if C is plus or minus 1, then locus of Z, it's a straight line. And if C is unequal to plus or minus 1, then locus of Z will be a circle. Now the question is, let the complex numbers alpha and 1 upon alpha bar lies on circles x minus x naught square plus y minus y naught square equals r square and x minus x naught square plus y minus y naught square equals 4r square respectively. If z naught satisfies the equation 2 mod z naught square equals r square plus 2, then we need to find the value of mod alpha. Now we are given that alpha, it lies on this circle, which we can write mod of z minus z naught equals r. So from here we can write mod of alpha minus z naught, it will be equal to r, and we square it, we'll write alpha minus z naught into alpha bar minus z naught bar will be equal to r square. So we can write mod of alpha square minus alpha z naught bar minus z naught alpha bar plus mod of z naught square, it is equal to r square, and that's our first equation. Now it is also given that 1 upon alpha bar, it lies on the circle mod of z minus z naught equals 2r. So we can write 1 upon alpha bar minus z naught whole mod, it is equal to 2r, or 1 minus alpha bar z naught whole square, it is equal to 4r square into alpha bar square. Now again, mod of z square is z into z bar. So we can write 1 minus alpha bar into z naught into 1 minus alpha into z naught bar, it is equal to 4r square, and mod of alpha bar is same as mod of alpha. So it will be simply mod of alpha square. Now we multiply it, we'll write 1 minus alpha bar z naught minus alpha z naught bar plus mod of alpha square into mod of z naught square, and it will be equal to 4r square into mod of alpha square, and that's our second equation. Now we'll subtract this second equation from first equation. So it'll be minus, plus, plus, minus, and minus. Now here alpha z0 bar will cancel, alpha bar z0 will also cancel, so we'll get mod of alpha square minus 1 plus z0 square into 1 minus mod of alpha square, and it will be equal to r square into 1 minus 4 times mod of alpha square. Now we can write this as 1 minus mod of alpha square into mod of z0 square minus 1, and it will be equal to r square into 1 minus 4 mod of alpha square. Now we are also given that 2 times mod of z0 square minus 1, it is equal to r square. If we cancel z0 square minus 1 with r square, we'll get this 2 here. So we can write this as 1 minus mod of alpha square will be equal to 2 minus 8 mod of alpha square, that is 7 times mod of alpha square equals 1, or mod alpha is equal to 1 upon under root 7, and that's your option C. Now here the question is, if there is at least one complex number z which satisfy both the equality and the inequality, then real values of parameter m are given by. Now radius, it must be positive, so we'll get this condition that m plus 5, it should be greater than or equal to 0. So that's our condition for domain, that is value of m is greater than or equal to minus 5. Now from all the possible values of m, we'll exclude all those cases when these two regions, they do not have any point in common. So there can be 2 such cases. Case 1. Now first we'll consider this inequality region. Now center is at 4 and radius is 3 units. And since there is no equality sign, we'll draw this dotted circle. So we are talking about all the points inside this circle, and then this other circle whose center is at m iota and whose radius is m plus 5. Now there will be no solution when C1, C2, it is greater than or equal to R1 plus R2. And I'm taking this equality sign here because points on this other circle, they are not included. Now what's C1, C2? C1, C2 is under root of 16 plus m square, and it will be greater than or equal to m plus 5 plus 3, which is m plus 8. So it will be 16 plus m square will be greater than or equal to m square plus 64 plus 16m. Now this m square will cancel. So we'll get 16m, it is less than or equal to 16 minus 64, that is m is less than or equal to minus 3. So that's our first case. Now the second case possible when they do not have any solution is when we have this circle and this other circle, and this inequality region, it lies completely inside this other circle. So for this one, condition will be C1, C2 will be less than or equal to R1 minus R2. Now C1, C2 in this case is again under root 16 plus m square, and it will be less than or equal to R1 minus R2. So it will be m plus 5 minus 3. So it will be m plus 2. Now for this, m should be greater than or equal to minus 2, and if we square it, we'll get 16 plus m square will be less than or equal to m square plus 4 plus 4m. Now this m square will cancel, so we'll get m should be greater than or equal to 3. So condition is m is greater than or equal to 3. So these two circles, they won't have any solution if m is either less than or equal to 3 or m is greater than or equal to 3. So they'll have at least one point in common for all other points. So if we take all of the points in this domain, all the other points in the domain are when the value of m lies between -3 and +3. So answer to this question is when the value of m lies between -3 and +3, and that's your option C. Now here the question is the real values of parameter a for which at least one complex number satisfies the equality mod of z plus root 2 equals a square minus 3a plus 2 and inequality mod of z plus iota root 2 is less than a square. Now we'll first find condition of domain, and condition of domain will be a square minus 3a plus 2, it should be greater than or equal to 0. Now we'll simplify it. This is 1 and 2. It is plus, minus and plus. So condition of domain will be either the value of a is less than or equal to 1 or the value of a is greater than or equal to 2. Now we need to find all the possible values of a for which these two regions will have at least one point in common. So what we'll do is we'll actually find all the possible values of a when they do not have any point in common. So they won't have any point in common in two cases. In the case one is when this circle whose center is at minus root 2 and radius a square minus 3a plus 2 and this inequality which is points inside this circle with center at minus iota root 2 and radius a square, they do not have any point in common, and the condition for this will be C1 C2, it should be greater than or equal to R1 plus R2. So C1 C2 is under root of root 2 plus root 2, which is under root 4, will be 4 and will be greater than or equal to R1 plus R2, and R1 plus R2 will be 2a square minus 3a plus 2. Now this 2 and 2 will cancel. It will be a into 2a minus 3 will be less than or equal to 0. Now this is 0. This is 3 by 2 plus minus and plus. So they won't have any solution when a lies between 0 and 3 by 2. But value of a should be less than 1. So this first case will be when the value of a lies between 0 and 1. And there won't be any solution in this second case when this inequality region, it lies completely inside this bigger circle. So for this case, condition will be C1 C2, it should be less than or equal to R1 minus R2. Now C1 C2 again will be 2 and will be less than or equal to R1 minus R2, and R1 minus R2 will be simply 3a plus 2. Now here we'll get this condition that a is less than or equal to 0. So there will be no solution when a is less than or equal to 1. So the values of a which are left in the domain are when the value of a is greater than or equal to 2. So all the values of parameter a for which there is at least one complex number in common will be when the value of a is greater than or equal to 2. So its answer should be a is greater than or equal to 2. A will be greater than 2 if we discard the possibility of a point circle. So answer should be a is greater than or equal to 2. Now here the question is, let A, B, C be three set of complex numbers as defined below. Now A is all z such that imaginary part of z is greater than or equal to 1. So we'll draw the axis. And then we'll draw this line, which is y equals 1. So A consists of all the points which lie on this line or above this line. Now second one is B represents this circle, which is mod of z minus 2 plus iota equals 3. Now this equation, it represents a circle whose center is at 2 plus iota and whose radius is 3 units. So it'll be this circle with center at 2 plus iota and radius equals 3 units. And this third one is some locus which is real part of 1 minus iota z, it is equal to root 2. Now 1 minus iota into x plus iota y, its real part, it is equal to root 2 and its real part is x plus y. So this third locus is a straight line which is given by x plus y equals root 2. So it will be this straight line which is x plus y equals root 2. Now first question is number of elements in the set A intersection B intersection C. Now we need to find all the points which lie in all the three sets. It should lie on this circle, it should also lie on this line, and it should also lie in this region. There is only one such point possible. So number of elements in this set A intersection B intersection C is simply 1, and that's your option B. So it is this point. Now the next one is, let Z be any point in A intersection B intersection C, then mod of Z plus 1 minus iota square plus mod of Z minus 5 minus iota square lies between. Now any modulus is distance. So it is distance between Z minus 1 plus iota whole square and plus this is Z minus 5 plus iota whole square. Now this is 2 plus iota and radius is 3 units. So this point, it will be minus 1 plus iota and this other point will be simply 5 plus iota. So this is some point, say P, and this is Q, and let the center be R, and let this point be T. So what we are asked is Z minus 1 plus iota whole square. So that means we need to find the value of PT square plus TQ square. Now since PQ is diameter of the circle and this angle will be 90 degrees, then from Pythagoras theorem we know that PT square plus TQ square, it must be equal to PQ square. And what is the value of PQ? PQ is diameter of this circle, which is 6. So 6 square is 36. So this value, it is 36 and it will lie between 35 and 39, and that's your option C. Now the next question is, let Z be any point in A intersection B intersection C, and let W be any point satisfying mod of W minus 2 minus iota, it is less than 3. Now W is set of all points lying inside this circle. So we have this W. Now we'll find minimum and maximum value of mod W. Now we know that minimum and maximum value, it will occur along line joining this origin and center of the circle. Now this distance from origin to 2 plus iota, it is root 5. Now this is minimum distance, so it will be 3 minus root 5, and its maximum distance will be root 5 plus 3, so it will be 3 plus under root 5. Now for this mod Z, it lies on the same circle, but on the positive side when the value of y is greater than or equal to 1. So this mod Z will be less than maximum value of modulus on this circle, which is 3 plus root 5, and it'll be greater than this distance, and this distance is root 2. So it'll be greater than root 2 but less than 3 plus root 5. Now here the question is, let S is the set which is intersection of S1, S2 and S3, where S1 is set of all points Z such that mod Z is less than 4. So this S1, it consists of all the points inside the circle with center at origin and radius equals 4. So this is your Z1. Consisting of all the points with center at origin and radius equals 4 units. Now S3 is set of all points in which real part is greater than 0. That means all the points inside this circle which lie on this first quadrant or fourth quadrant. And then this S2, which is imaginary part of Z minus 1 plus root 3 iota upon 1 minus root 3 iota, it is greater than 0. Now we need to find imaginary part of this. Now it will be Z upon 1 minus root 3 iota and then minus 1. We can write this as x plus iota y into 1 plus root 3 iota upon 4 minus 1. So its imaginary part will be root 3x plus y by 4 and it is greater than 0. So this S2, it represents all the points which satisfy this condition that root 3x plus y is greater than 0. So it will be this straight line y equals minus root 3x, and if we put x is 4 and y is 0, so it will satisfy this inequality. So all the points in this set S, they will lie inside this region, and this angle is 90 and this angle is pi by 3. Now the first question is, we need to find minimum value of mod of 1 minus 3 iota minus z, which we can also write as z minus 1 minus 3 iota. Now this is nothing but distance between z and this point, which is 1 minus 3 iota. Now 1 minus 3 iota, it will lie somewhere here. So this point, it is 1 minus 3 iota. Now we need to find minimum distance between this point and all the points in this region. Now we know that the point which is closest to this point, it will be this perpendicular on this line, which is root 3x plus y. So we have to find this minimum distance. So it will be minimum when this distance is minimum, and for that we need to find this perpendicular distance of this line root 3x plus y equals 0 from this point 1 comma minus 3. So it will be root 3 minus 3 upon under root of a square plus b square, which is 2. So this minimum distance will be 3 minus root 3 by 2. So minimum value of this modulus is 3 minus under root 3 by 2. Now question number 27 is, we need to find area of this region. Now area of this region S will be, now this angle, it is pi by 2 plus pi by 3. So it will be 5 pi by 6. Now theta upon 2 pi into pi r square, and r square in this case is simply 16. Now here pi and pi will cancel. This is 8, this is 4 and this is 3. So it will be 20 pi by 3, and that's your option B. Now here the question is, let ABC be vertices of a triangle lying on a unit circle z equals 1, and AD is altitude of triangle ABC meeting the unit circle in E. So we have this unit circle with center at origin, and then we have this triangle ABC. Whose vertices are Z1, Z2 and Z3, and we are given that mod of Z1 equals mod of Z2 equals mod of Z3 and is equal to 1. Now it says if AD is altitude of this triangle and it meets this unit circle at E, then the first question is orthocenter of this triangle ABC is. Now first thing, we'll find its centroid. Now centroid is at Z1 plus Z2 plus Z3 by 3, and it is given by, say, G. Now since ABC, they lie on a unit circle with center at origin, its circumcenter is at origin. Now once we have G and O, we can find H. Now we know that G divides OH in the ratio 1:2. So we can write G equals 1 into H plus 2 into O upon 3. Now G is Z1 plus Z2 plus Z3 by 3. So we can write Z1 plus Z2 plus Z3 by 3. It is equal to H plus 0 upon 3. So H is at Z1 plus Z2 plus Z3. So orthocenter of this triangle is Z1 plus Z2 plus Z3, and that's your option A. Now B is, this E is given by minus Z2 Z3 upon Z1. Now suppose this is Z4. Now we know that this H is Z1 plus Z2 plus Z3. Now we can write equation of AD, and equation of AD is given by this determinant Z, Z bar 1, Z1, Z1 bar 1 and Z1 plus Z2 plus Z3, Z1 bar plus Z2 bar plus Z3 bar and 1, and it must be equal to 0. Now E, it lies on this line, so we can write this as Z4. Now what we'll do is we'll write R1 as R1 minus R2 and R3 as R3 minus R2. So we can write this as Z4 minus Z1, Z4 bar minus Z1 bar 0. This is Z1, Z1 bar 1, and here it will be Z2 plus Z3, Z2 bar plus Z3 bar and 0. It must be 0. Now we'll expand it about this third column. We can write this as Z4 minus Z1 into Z2 bar plus Z3 bar, and it must be equal to Z2 plus Z3 into Z4 bar minus Z1 bar. Now each of this ZR, they lie on this unit circle, so that means mod of ZR equals 1. Now if we square it, then ZR into ZR bar, it is equal to 1. So we can write ZR bar as 1 upon ZR. So we can write this as Z4 minus Z1, and this is 1 upon Z2 plus 1 upon Z3, and it is equal to Z2 plus Z3, and this is 1 upon Z4 minus 1 upon Z1. Now if we solve it, we can write Z4 minus Z1 into Z2 plus Z3 upon Z2 Z3 will be equal to Z2 plus Z3, and this is Z1 minus Z4 upon Z1 Z4. Now this will cancel. It will also cancel, but we'll have this minus sign here. So from here we can say Z1 into Z4 is minus Z2 Z3, or value of Z4 is minus Z2 Z3 upon Z1. We have proved this result using one more method. I'll provide the link to that video in the description below. So that means option B is also correct. Now this third one is if Z1 square is Z2 Z3 and Z2 square is Z3 Z1, then this triangle ABC is equilateral. Now we multiply them, we can write Z1 square plus Z2 square will be equal to Z1 Z2 into Z3 square. Now we can cancel this Z1 Z2. So from here we can say Z3 square is Z1 into Z2. Now we add all of them, we can write Z1 square plus Z2 square plus Z3 square, it is equal to Z1 Z2 plus Z2 Z3 plus Z3 Z1, which is the condition for an equilateral triangle. So that means this option C is also correct. Now this option D is if Z1 plus Z3 is 0, then ABC is right angled triangle. Now in option A, we have already proved that orthocenter of this triangle is Z1 plus Z2 plus Z3. Now if Z1 plus Z2, it is 0, then orthocenter of this triangle ABC, it is at Z1. Now when orthocenter is at A, that means this triangle is a right angle triangle with angle A as 90. That means this option D is also correct. So the correct options are A, B, C and D. Now here the question is, consider a complex valued function fz, and it is given by 1 upon z minus iota. Now it says locus of point fz as z lies on real axis is. Now if z is real, say z is x, then we can write fz as 1 upon x minus iota, and this is equal to say u plus iota v. Now we can write this as x plus iota upon x square plus 1, it is equal to u plus iota v. Now u is x upon x square plus 1 and v is 1 upon x square plus 1. So we can write x as u upon v. Now we put the value of x here, we can write v equals 1 upon u square upon v square plus 1. So it will be u square plus v square minus v equals 0, which is x square plus y square minus y equals 0, which is equation of a circle. So answer to this question 42 is this option B. Now question number 43 is, if FA, FB and FC are vertices of a triangle, ABC belongs to R minus 0, then area of this triangle is. Now we know that if ABC they are real, then FA, FB and FC they lie on this circle. Now for this circle, center is at 0, 1 by 2 and radius is also 1 by 2. So we'll have this circle, its center at 0, 1 by 2 and radius equals 1 by 2. Now we need to find maximum area of this triangle which can be inscribed in this circle. Now we know that in a circle, area of triangle is maximum when the triangle is an equilateral triangle. So this triangle, it must be an equilateral triangle. So we need to find area of this triangle will be 3 times, and then area of these 3 triangles will be 1 by 2 into 1 by 2 into 1 by 2. So this maximum area will be 3 root 3 by 16, and that's your option C. And question number 44 is, if FA, FB, FC and FD where A, B, C, D are R minus 0 vertices of a square, then we need to find area of this square. Now again, since A, B, C, D are real, this square will lie inside this circle. So we have this circle and then we have a square which is inscribed in this circle. Now let the length be L. So we know that root 2L, it must be equal to length of diameter, which is 1. So value of L is 1 by root 2. Then area of square will be simply L square and L be 1 by 2. Here this square is always constant and is independent of A, B and C. That's your options C and D. So this area, it must be 1 by 2. Now in geometry of complex numbers, there is something called as inverse points with respect to a circle. Now if we have a circle with center O and radius rho, so we have a circle whose center is at O and its radius is rho. Then P and Q are said to be inverse with respect to circle if O, P and Q, they are collinear. So these 3 points O, P and Q, they must be collinear on the same side of O, and OP into OQ, it must be equal to rho square. So that is the definition of inverse points with respect to a circle. Now say for example, we are given that C is the center of a given circle, Z minus C equals R. So we have this circle whose center is at C and radius is R. Now it says A is a point represented by complex number A inside the circle and B is a point represented by complex number B outside the circle. So we have 2 points A and B. One of them, it lies inside the circle and it is represented by A, and this is represented by B. And it says CA into CB, it is equal to R square. That means A and B are inverse points with respect to each other. Now we need to show that B equals C plus R square upon A bar minus C bar. Now we have 2 points A and B. Suppose CA is M and CB is N, and we are given that CA into CB is R square. That means M into N is R square. Now this distance is N minus M. So from here we can write A equals MB plus N minus MC upon N. Now we can write NA equals MB plus N minus MC. We can also write this as NA equals NC plus M into B minus C, or we can write B equals C plus N by M into A minus C. Now we can write N as R square by M. So we can write this as B equals C plus, now it will be R square by M square into A minus C. Now what's M? M is distance between AC. So we can write M as mod A minus C. So it will be B equals C plus R square A minus C, and M square is mod of A minus C square. So there will be A minus C into A bar minus C bar. Now I will cancel. From here we can write B equals C plus R square upon A bar minus C bar, and this is what we need to prove.